who will be presenting on the case studies, and real world applications. Dr. Bandopadhyay is a distinguished expert in the field, and her session promises to provide us with practical insights and valuable lessons from real world implementations of AI and healthcare. As we have explored the fundamental concepts and ethical considerations over the past few days, today's session will bring theory into practice, and today's topic, case studies and real world applications, is crucial because it bridges the gap between theoretical knowledge and practical applications. Dr. Bandopadhyay will discuss various case studies demonstrating how AI models have been applied in real world healthcare scenarios. We will learn about the successes, challenges, and lessons learned from these implementations. And by examining these case studies, we will better understand the practicalities of deploying AI in healthcare, the importance of making AI systems explainable to build trust and transparency, and how to navigate the complexities of real world environments. This event is organized by the Department of Computer Science and Technology, the Department of Artificial Intelligence and Machine Learning, and in association with the Department of Computer Science and Engineering at JIS College of Engineering, Kalyani Nadia. Our collective aim is to provide you with comprehensive knowledge and practical insights that can be applied in your own teaching and research endeavors. Dr. Oishila Bandopadhyay received her PhD degree from IIEST Shibpur, Howrah. She has worked as DST woman scientist in advanced computing and electro microelectrics unit of ISI Kolkata, and presently she is working as assistant professor of CAC in IIIT Kollani. She has several publications in reputed index journals and international conferences, and her research interests include medical imaging processing and computer vision. We encourage all participants to engage actively with Dr. Bandopadhyay, ask questions, and share your perspectives. This session is a great opportunity to learn from real world experiences and to understand the impact and potential of explainable AI in healthcare. Without further ado, please join me in welcoming Dr. Oishila Bandopadhyay. Thank you, and let's dive into today's session. Ma'am?
Thank you, madam, for the brief introduction. Let me start with the discussion. I will also expect the participants to interact because, as we all know, this particular topic is a very new topic for AI community, and people are mostly trying to understand why the system is behaving like this. I hope from last 3 days discussion, the basic idea of what explainable AI is trying to do, you all have from the other speakers. So I will also have a little introduction of the basic things, and then I will move to few case studies. As in the introduction, it was already mentioned, our main focus is to understand how these things are used for explaining the system, mostly for healthcare. So let me share the presentation first. Is the screen visible? My screen visible?
Yes, ma'am, it is visible.
Okay.
Yes, ma'am.
Okay, so the definition of explainable AI already, I hope it is already discussed by multiple speakers. But again, I am just mentioning it to make a continuation. The target is a setup process and methods that allows human users to comprehend and trust the results and output created by the machine learning algorithms as per the definition given by IBM there. Because this group is working with explainable AI for a long time. So the main target is to allow the users trust and comprehend. That is the most important part, because this explainable AI in case of healthcare, why it requires That is the thing we are trying to understand. And in case studies also, it will be shown that how these things are actually used in practice. Just look at this particular example. I don't know whether it is already discussed or not, but this is a very interesting example or interesting finding reported in 2021. It was done by, the study was done by a group of doctors, Edward Corrett and his group, and finally it came up as a scientific report. The thing is, they were studying the fundus images of retina, and they are trying to identify some disease present in that retina image or not. So you can see this is the image taken from their paper. Original image, these are all fundus images, and this is later these were generated using the saliency map. So the main thing was they are trying to identify whether the retina is healthy or retina is having some disease. But at the same time, they did another study that whether the system can predict the sex of that patient from the retina image. And most surprisingly, it came up that in the ground truth, they are giving the retina image and male female, that actually they are giving the retina image and related patient information. So in that, sex information is also there and the male female category was mentioned. And later, suddenly they thought that why can't we try to find out whether the unknown retina image also the system can predict. And it came up that system is predicting the gender of that particular patient. Most of the cases very correct. But now this was most surprising because they were the group of doctors and they had the domain knowledge that till that date there were no study in clinical literature which directly mapped the sex of a particular patient with the retina. People never thought of this because these are two totally irrelevant information. And doctors, when they are the eye specialists, they were mostly using these fundus images and they were mostly looking for the disease, not for the gender of that particular patient. But when it came up, then the question arises that how this black box deep learning process can identify the sex of that particular patient. There was no indication of name or other thing, only the image was the image. So this was one situation. Another situation was, I don't have that image here, I'm just explaining, lung X-ray, chest X-ray actually. The series of chest X-ray, the doctors were trying to study for some disease, healthy X-ray and diseased X-ray. And they identified that while the training, the system was working very nicely and accuracy was almost 100%. Validation also the same thing. But for test cases, the accuracy dropped drastically. Now, chest X-ray, variation in chest X-ray can't be that much that the accuracy can be dropped. So they were surprised to understand to their findings that why that accuracy dropped that much. And later, when they look at the test images, they identify that in that chest X-ray test image data set, many chest X-ray images were marked with some small red pin mark, maybe locating a particular point in that X-ray. And the system considered that mark as the point of disease. Now, the thing is, the way this first case, chest X-ray case, the way this black box AI system is trying to identify that it is healthy or disease. That is one point. Manually, when we go through all the images, it is noticed that just some chest X-rays which are having those red mark, pen mark, which was done for some other purpose, but that came in that image digital image plate. That was the culprit. Because of that red mark, the system misclassified it. Okay, that is understood that the input image had some problem. But this case, where the gender of that particular patient is identified from the retina image, people were actually very much surprised. And then they thought about developing a system through which they can identify that which portion of the image is actually studied by, or which portion of the image the features are actually focused by my deep learning system to classify the image. Whether it is the retina boundary, whether it is the veins within the retina, or the optical nerve source, which portion. And when they started this XRI saliency map I will explain later. Basically, this is a region-based study or mapping that which portion is contributing. They identified that this portion, you can see each of the image, it is marked that which all regions, it has appeared with the different color. Which all regions are actually the region of interest for the deep learning system. And then they are satisfied with the result because it is clearly identified that this deep learning system is basically focused on the main source of optical nerve and their initial distribution for classifying the gender. That means they have identified some similarity among this distribution and the gender of the patient, which was by that time, which was unknown. So, and you can see the confidence score here for male and female. The confidence score in most of the cases is showing more than 80%, which was quite encouraging. So this type of study, later they reported is as the predicting sex from retinal fundus images photograph using automap deep learning, and it was published in 2021. It's not very old paper. So this type of study actually forced the research community to concentrate on the explainability in healthcare, because in healthcare, what happens? Doctors gives their ground truth for any medical image or any patient information collected in tabular form. Now, when doctor is giving the ground truth, doctor has some theoretical knowledge, some practice, experimental practice outcome, through which they can predict that these parameters are giving these values, means this patient might be suffering from this problem or this disease. Similarly, from medical image, there are certain signs through which, or certain abnormality in image through which doctor can identify that this image is not a healthy image, it is the diseased image, and what type of disease. Now, we want to ensure that when we are using this deep learning as a black box, because deep learning, in machine learning cases, there are chances of interpreting the thing, but machine learning techniques, algorithms, but in deep learning algorithms, that chance is relatively low. So when we understand that deep learning, we can't say that which portion of the particular image is point of focus, or which portion of particular image is actually considered by the deep learning architecture, then we can't say confidently that although it is giving correct result as per expectation, it is working just like the way human is classifying this or doctor is classifying this. It may consider some other location, some other feature also to classify or to take the decision of the system. So to gain the confidence on the result generated by the deep learning models, this explainability is required. And that is the main focus of this series of lectures. And I hope this is also discussed already, though I want to just reiterate when we say explainability, another very close term is interpretability. Now, what is the difference between interpretability and explainability? Interpretability is that techniques that are part of the model architecture and definitely computationally fast, whereas explainability, that is the model agnostic, computationally intensive, and based on feature values and predictions. So, if we say the known algorithm we want to classify whether it is interpretable algorithm or interpretable technique or explainable, then you can find out the most of the machine learning techniques like decision trees, linear regression, or logistic regression, they comes under the interpretable models. Why? Because in case of decision tree, mostly you are using the probability values. And logistic regression or linear regression also, you are mostly working with the probability, you are mostly working with the features, and you are trying to classify that which particular class it belongs based on some threshold. So there you have the clear explanation or you have the transparency to comment on the result generated by the system. That's why we can say this is interpretable. Whereas in case of neural network, random forest also to some extent, neural network, ensemble networks, and deep learning architectures, there most of the cases we have no detailed information about which particular CNN layer is focusing on which particular region of my input image or input data, or which particular ANN layer is focusing on which particular set of input data, which values of the input data, or whether the input data is considered properly as desired by my ANN or by my CNN. So that's why this part we need the explainable models, or this part comes under explainable models because these are less interpretable. So mostly machine learning based models are more interpretable, linear non-linear models, non-linear or logistic regression models, and non-linear functions which are incorporated in case of deep learning models, they are less interpretable. So we can classify the explainable AI in two categories: directly explainable model, which are actually the interpretable models that are not coming within the scope of XAI we are trying to discuss. So these models includes the linear model, decision-based model, rule-based model. And we have the post hoc explainability. Post hoc explainability is you have the data, you have the learning done, and you are generating the output. Now, based on that, you are trying to, based on the outputs and the input data, you are trying to explain the model. That is post hoc explainability. So, deep neural network and ensemble models, this comes under the post hoc explainability. So, this is the we can say the broad classification. The post hoc explainability, that also can be of type global or local, that is explaining the model, that can be termed as the global, explaining the decision, one particular decision or the decisions that comes under the local, and inspecting the counterfactual, that also another type of explainability, post explainability, that is studied by the research groups. I have mentioned most of my references because I have taken many images from different papers, so I have mentioned most of my references at the end. Now, this also is taken from this paper, Mavelli et al. With the post-hoc explainability for ML models. You can see the different methods or techniques are mentioned here with the local explanation and global explanation. Among that, there are feature importance, rule-based, saliency map, prototype-based, counterfactuals. Those comes under local explanation. Now, I think some of these techniques are already discussed. I am just revisiting it because I will discuss application of some of them in my case studies. So, feature importance, the explainer assigns to each feature an importance value which represents how much that particular feature has importance for the prediction under analysis. Say you have a particular group of patients with their body mass index, BMI value, their glucose level, their RBC, WBC counts. So all this type of clinical information for patient. And you are trying to predict the risk of heart attack. Now, for you have say 10-15 features. So among those 10-15 features, all might not be participating in the prediction, or all might not be that much importance, having that much importance for prediction. So feature importance, basically focus on that. The feature features are actually contributing in what score or what percentage. As it is patient specific, we can say one particular prediction and we can analyze the features for that particular case. So it comes under the local explanation. Similarly, in case of rule-based, the explicitly state the decision support system's decision boundary between the given and the contrasting advice, which can be viewed that if then else type of statement, like decision tree we are doing. Another interesting is saliency map. Saliency map generally used for image and video processing applications and is supposed to show what part are most important to a network decision. I will show you some of the outcome of my case studies using saliency map. There are prototype-based systems where a prototype is an object representing a set of similar records that the user can easily view, understand, and appreciate that similarity to other validation samples. And counterfactuals. Counterfactuals is also an interesting type of explanation. It explanation that provides a link between what could have happened had the input to a model been changed in a particular way. A very common example, I don't know whether it's already discussed or not, for counterfactuals that comes under, say, a bank is giving loan to their customers. Now, many customers applied for loan and based on their savings amount, based on their monthly credit in that account, and based on their age, service left, all these factors, bank is deciding whether the loan will be awarded or not, loan will be granted or not. Now, it has been observed that with similar kind of this parameters values, like with the almost similar service years left, similar type of bank balance, similar type of salary, one person is getting the loan, another bank has refused, or the AI system working in the bank, it has refused. Now, the list of features I have mentioned, they are not directly contributing to that decision, because we can say that all these parameters are same for both the cases. Then what is contributing? So that is a situation of counterfactuals, where you are trying to find out that it is supposed to give the loan but is not giving, so why it has happened. And in that type of situation, it may be identified that that particular person is having debit already. If he is having debt, then definitely there is a chance that he will not be able to he will not be able to return that loan amount. So bank or AI system is refusing. So apart from the parameters we have mentioned, there are other parameters which are here, which are playing the role. So this type of situation, also it is a local explanation because it is one particular case basis we are explaining. So that's why this is a local explanation model. So this is also another interesting model which people used to apply for explaining the AI system. Now coming to global explanation mostly trying to focus on the design part. So collection of local explanations. Pick a subset of k local explanation to constitute the global explanation after generation of a local explanation for every data instances using one of the above approaches. So each of the local explanation methods we have mentioned, any of them can be used, and then collection of local explanation is used for explanation. So that is the approach. Second one is the representation based, where the derived model understanding by analyzing intermediate representations and the determined models reliance on concepts that are semantically meaningful to human. So that is the representation based case. Model distillation is leverage model distillation to learn feature shapes that describe the relationship between input features and model predictions. And summaries of counterfactuals that actually construct the global counterfactual explanation, which provide an interpretable and accurate summary of the cases of our entire population. So these are some of the methods. If you check this particular link, you will find a very detailed discussion on each of them. So those who are interested, they can explore this. It's very useful. And this particular image is showing the approaches, what type of data and what type of approach or algorithm can be used. Like for tabular data, it has been noticed that many people have used this explainable AI using for tabular data feature importance based explanation, because I have said that which feature is contributing how much. It is easier to identify in case of tabular data. Again, rule based explanation, prototype based explanation, and counterfactual explanation. So these are mostly applied for tabular data. Then for text data, Saliency-map visualization is possible. Then input reduction and prototype based explanation. These are mostly used for text data. For image, definitely Saliency-map, as we have mentioned that Saliency-map visualization is very important for medical image. Then Shapley value important and concept attribution. Concept attribution is also used for medical image. Another type of data, that is a time series data. Time series data means we are getting the weather data, which is time series data. Your satellite images, those are also time series data. So that type of cases, if you want to go for the explainable AI, you will be able to generate the relevance heat maps to explain it, then prototype based explanation and patch based classification. So these are mostly covering the time series part. What about the performance? So we have the deep learning model, we have the machine learning or statistical models, and there are graphical models, ensemble and random forest and decision trees. So all those are there. So if I try to plot, this is already reported by Gunning in 2016, that if you try to plot the learning performance with explainability, you can see that learning performance is much less where your interpretability or explainability is very clear, like decision tree or like random forest. So random forest, the learning performance you can compare, learning performance is higher, whereas your explainability is much less. And the lowest explainability is in case of neural networks and deep learning. So that's what we are discussing till now, that interpretable models are mostly the machine learning models where the learning accuracy is much less compared to the deep learning or neural network models, but at the cost of explainability. Because explainability has reduced significantly when we are going for the neural network models. Now, in post-hoc explanation, there are few approaches which are very popular approaches. So, I am mentioning 2 or 3 such approaches, and then we will go for the case study part. So, in feature importance based explanation, under feature importance based explanation, as I have mentioned, this comes under the local explanation. So, 2 very popular approach. One is line, that is local interpretable model agnostic explanation. This was reported, or you can say the developed by Ribeiro and his group in 2016. And this agnostic approach that builds a sparse linear proxy model to get insight on a local decision once whole model is learned. So that is most important, that when this particular approach we are applying, here the case is when your whole model is learned, then this particular approach is used, line approaches can be used to identify the which portion of the or which features are actually used for classification. Similarly, another approach, that is SHAP, that is Shapley additive explanations, proposed by Lundenberg and his group in 2017, that assigns each feature an importance value for a particular prediction and fairly attributes the prediction to all features. And then it tries to identify which all features are contributing. Because this is a feature importance based explanation. So definitely the main focus is which all features are contributing more in taking the decision. Here is one example of SHAP value based model. You can see it's a black box model which is taking the inputs as age, BMI, blood pressure, and sex, and generating the prediction, what is mortality risk score. That is the prediction. So you don't know which all among these 4 are contributing for this score. Which way these scores are contributing, these values are contributing, and these features are contributing to generate this score. Now, if you come to the tree explainer, which is the explainable model for used for this explaining this black box, you can see all these 4 inputs are used or features are used, and a particular value is assigned. As we have mentioned in the previous slide, that assign each feature the importance value for a particular prediction. That's what is done here. A particular value is assigned, like for mortality risk score, this sex value is assigned -2, whereas blood pressure +3, BMI 0.5, and age 2.5. And with this, it has calculated the mortality score value 4. So it assigned the values, and then now it becomes a white box because it is clearly shown that which all features are contributing more or having more weightage. We can say it's kind of weightage value. So which are features are having more weightage to generate the decision. So once the model is learned and you are having the input attributes and you are having the prediction result, then for the SHAP model or for the explainable model, the similar features are used, same features are used along with the weightage given, and is trying to generate the values which are already predicted by the black box model. And then it will be clear that which portion is actually contributed. So the study was done with another set, that is using the SHAP values, that is local explanations for the data sets which are having the mortality, kidney and the hospitalization data. And they used the black box as well as the tree explainer and use the local explanations in the SHAP value, and then find out the model summarization. So combining the local explanations from many samples, and this can lead to the global model insights. So model summarization, feature dependency, interaction effects, model monitoring, and explanation embedding. So all this can be done after the local explanations. Individual local explanations are done using local explanation techniques followed by the global case. So this is about the feature-based explanation. So for feature-based explanation, mostly these two are the most popular techniques, the line and the SHAP. And as we have shown in the previous case, that SHAP and line, all this comes under feature explanation, which is a part of the tabular explanation. So in case of medical data, if my data is available or features are available in tabular form in the numerical values or the alphanumeric values, we can go for the feature explanation based algorithms to explain that ANN. Now next one is the rule-based explanation. In rule-based explanation, there are different approaches, like anchors the approach proposed by Ribeiro et al. In 2018, and this explains the behavior of complex models with high precision rules representing the local sufficient conditions for prediction. And there are models like the model proposed by FDP et al. In 2018. It learns a local interpretable predictor load on a synthetic neighborhood generated by a genetic algorithm, and it derives from the logic of local interpretable predictor a meaningful explanation consisting of a decision rule and a set of contrafactual rules. So these are the two popular approaches used under the rule-based explanation. Now, if we are focusing on the images, medical image or the images used in healthcare, so saliency map is the most important. Saliency map can be used for text data as well as for image data. There are different approaches under saliency map. First one is layer-wise relevance propagation, Bach et al. Proposed in 2015. And it assumes that the classifier can be decomposed into several layers of computation. And such layers can be parts of feature extraction from image or parts of a classification algorithm run on computed features. So the layers can be considered as a part of feature extraction from the image, and how we are extracting features or which all features the neural network focused on when it is considering the image. We all know that the features, like most low level feature to the abstract level feature, considering the edge boundaries, the pixel intensity values, the colors, and the corners. All these things are considered by the neural network. So this layer-wise relevance propagation actually focus on the features extraction performed from the image or the parts of the classification algorithm running on that computed features. And another most important part is integrated gradients. This was proposed in 2017 by Sundararajan et al. This computes the gradient using the gradient operation. Now, computed gradient is a very common approach computing the gradient of different regions of your image, and very useful technique also to identify that which all portions of the image, medical image, is considered for classifying a particular disease, which is very important for the doctors, that whether the AI system is performing the classification the same way the doctor look at the image and perform the classification. Because until and unless we apply these techniques, we have no way out to identify whether the system is performing or system is using the features the similar way as human being use it. Now, this integrated gradients, if you are using Python utilities, you will find a very common term used here, GradCam analysis. That GradCam analysis is basic nothing but the integrated gradient algorithm. And GradCam, GradCam++, there are several algorithms with the gradient calculation, and these are very simple. Just with the functions, you can find out what is happening with the input image. I have given one case study that actually we did, my PhD students, he did in his thesis. So the main target was to identify the grade of the osteoarthritis affected knees. So the input was knee X-ray. Now, system was classifying the grade 0, grade 1 and grade 2. Grade 2 is the severe osteoarthritis, grade 1 is the moderate, and grade 0 is just the early stage. Now, the classification reported in most of the literatures, grade 0 and grade 2, people have classified very clearly with very high accuracy. But when you introduce grade 1 also, the accuracy reduced. So we perform a GradCam analysis to identify that whether my deep learning model is also working the similar way doctors look at the knee image, knee X-ray image, and try to identify which portion of the X-ray is having the abnormality. So you can see here the color change. This red color is actually indicating the portion or region of interest used, or the region focused by the CNN model. From clinical point of view or medical point of view, this osteoarthritis is detected based on two things mostly. One is the reduction in gap between these two bones, and another thing is the presence of osteophytes. Osteophytes means the sharp edges. Actually, our bone portion destroy with age, and some of the region becomes very sharp. That is known as osteophytes. So, presence of osteophytes and reduction in gap. So, in early stage, the presence of osteophytes is the main indicator of osteoarthritis. Once the arthritis situation deteriorates and the knee becomes from grade 0 to grade 1 or grade 2, Mostly in grade 2, the gap reduced, and that becomes the main cause of suffering. So you can see in the grade 1, here the model also concentrate on this sharp part, which is basically the osteophytes for both the images. Whereas in grade 2, you can see the model is not focusing on this one. The reddish part appears near the gap because there is a change in gap. You can see the gap in this region and the gap in this region. For both the images, as the gap reduced, the model is focusing on the gap, whereas the first one, the model is focusing on the osteophytes part. So this was only one study we did that time during his thesis. But the message I want to convey is this type of analysis is very useful to find out whether the way your system is doing the classification for your improved medical image, whether that is the same thing acceptable by the medical community or not. Because these deep learning models are data driven in many cases. And if you are having a very good data set with different similar proportion of different classes of images, definitely you can expect a good result. But if you are having a biased data set with very less healthy image, more diseased image, or vice versa, you may have a biased decision. So when we are focusing on, we are trying to go for explainable AI, there itself you can get the answer that whether the particular area of interest is considered by AI or not. So this is one case study we have done during our research. Now, as I have mentioned a few technique, this diagram is very nicely given in the paper Shew et al. It's basically a survey paper, survey on medical explainable AI, recent progress, explainability approach, and human interaction and scoring system. It's published in 2022. If you try to look at this diagram from the leftmost part, you can see the support vector machine, linear SVM, polynomial SVM, Gaussian RBF, so different kernels of SVM, then deep belief network, deep rule forest. All these are actually coming to machine learning part. Along with that, we can have the CNN, RNN, LSTM. These are my deep learning part. So these constitute my AI/ML methodology. And which are evaluation techniques we are using? We are using the p-value, scoring system, then accuracy. All these things are basically the evaluation technique to identify how good my model is working, how much accuracy it is giving, or MSC value, those things we are using. So in medical image analysis, if we keep this entire system with the evaluation technique and the AI/ML technique in one side, then we can see in the other side we are having the data pre-processing and we can have the explainable. You can see this model with the data. We can have GradCam, which is basically the gradient-based analysis. I have already discussed, shown in the previous slide. And GradCam can have different variations like guided GradCam, response cam, multi-layer cam. Then for data preprocessing, another set is the SHAP, which is mostly used for the tabular data. Which feature is contributing more? If you want to understand that, you will have the SHAP and line approach. The statistical functions, mode, all these are the approach. And different types of tests are mentioned here under the statistical function. So mostly these two are these are portion we are having the shape, breadcrumbs, mode. These are the explainable AI components. And then you can have LRP with LRP, you can have LRP diploid, LRP bilab, LRP DNN or LRP CNN. So this part can be used for to explain the behavior of these models in presence of data. That's why this data preprocessing part is mentioned here. So if you are working with the medical image or you are working with the medical data, and it is very important to understand that whether the data is interpreted by your system the similar way the doctors are trying to classify the thing, then any of this technique, depending on what type of data you are using, you can use that. Coming to another case, this is another case study proposed by Lodison et al., published in 2020, that is explainable artificial intelligence model to predict acute critical illness from the electronic health records, and is published in Nature Communications. So the thing is, they have identified, actually this was also done by a group of doctors and one lady, she was basically working in the emergency unit. So they identified that there are few parameters, body parameters, which gives the indication that whether the patient is moving towards critical illness or not. As those doctors are working in the emergency unit with serious patients, so it was very important for them to have some prediction methodology through which directly they can just put the parameters and find out whether the patient is moving towards the critical illness like kidney failure or heart failure kind of thing, or patient's health situation is under control. So they tried to develop the model and then move to the explainable model also, explanation model also. So they use the parameters. Mostly the patients, they work on the ICU patients. So they use the parameters, that is serum creatinine, then kidney EG, potassium, albumin, all these with the patient data, and fit to the model, their prediction model. At the same time, the same set of parameters fit to the explanation model. And with the prediction model, when it is predicting the acute kidney injury of 78%, they are feeding it to the explanation model and checking which all are contributing more. And it can be identified that the blue color parameters, those are marked as the parameters having less contribution towards the decision that patient is critical, whereas the red color parameters, those parameters are having more contribution towards this decision. You can go through the detailed paper to identify what type of system they actually propose. This XAI EWS, that is basically the explainable AI for critical illness prediction, the model they propose for prediction. Now, another decision support system, which is mostly used with clinical decision support system, that is the CDSS. This explainable AI with CDSS or clinical decision support system is also used. Now, this is reported by Du et al., published in 2022. The title of their paper was The Role of Explainable AI in Advice Taking from a Clinical Decision Support System, a comparative user study of feature contribution based and example based explanation. So they studied a machine learning based CDSS developed for prediction of gestational diabetes mellitus. So basically, the probability of having diabetes among pregnant women that was studied. And the model can predict this GDM is based on 5 features or 5 parameters. Family history of that particular woman, age, body weight, serum white cell count, and gestational age at first antenatal visit. So this clinical decision support system or CDSS, they want to design for this particular target, that what is the prediction, whether the patient is having high risk for GDM or low risk for GDM. And at a threshold of 0.5, it classifies the pregnant woman into those at high or low risk developing a GDM. Now, this is the thing they have reported in that paper. One particular case they have taken, the patient named say Anna, is reporting low risk of developing GDM. Now, this can be explained by this plot, which shows that the contribution, the range from -1 to 1 of each feature to the decision, and this red bar, this range is from -1 to 1. They have used the SHAP value. That means individual parameters, their contribution cases with some weight assigned, and then the total summation for each of the local, that is also used for the model level. So here red bar indicates the feature increases the risk of GDM, whereas the blue bar indicates the feature that decreases the risk of GDM. So age with the serum white cell count and body weight, this all appears with blue bar, even family history also, because this for this particular patient, family history is no, so it is reducing the risk of GDM. Age is low, 27, so it is reducing the risk of GDM. Serum white cell count is also moderate, body weight is also not that high, but gestational age is 13 weeks, and that is marked as the red bar. So with the gestational age, that can contribute in predicting high value of GDM. So basically, that is the only parameter here which is contributing to the high value. Now, why this is important? This study is important because if we are not performing any kind of explainable part, only we are taking all these parameters and using our model to predict, then say for 1,000 cases you are getting the correct prediction for a particular data set. Now you have taken a separate data set, maybe from different country with different set of these values. So this entire prediction may not, the entire model may not give you the correct answer. If the model is focusing on this body weight, white cell count, or age, because those are not the correct factor. Clinically, those are not the correct factor always contributing increase in GDM. Basically, they are contributing to decrease in GDM. Now, if we perform this type of study, then only we can conclude that, okay, the model is also considering the point which is a clinically valid point for considering the chances of increasing GDM value. So, if we try to use the model just like a black box, mostly in case of healthcare and medical decision-making systems or clinical decision-making systems, then there is a high risk that model may not be interpreting the thing or may not be focusing on the features we are trying to use for our clinical purpose. So it is very important to understand that which all features the model is using, but which all features the model is focusing on. And as you have noticed, I have shown in that case one that they have used the they have used the CAD-CAM analysis because the input is the medical image. Or you can say video also the same thing can be done. Whereas in case of case 2, they have used tabular data and shape or line can be used to in form of explanation module to identify whether these parameters are taken properly or not, whether features are considered properly or not. Similarly, the third case also, it is used mostly the tabular data, and that can also be used to identify whether these cases and these particular features are contributing or how much they are contributing. Now, as I have already shown that these high risk and low risk cases where the parameters which are contributing more that can be identified or the parameters which are contributing less that can also be identified to find out that which portion is actually working on or actually used by the model to generate this particular output. I'll just try to interact with the audience that to understand that how this type of work can help them. Before that, let me try to quantify how these parameters are actually can be estimated. Like I am applying a particular explainable model, like the case 3 they have used. They have used the explainable model chat and they are trying to identify which all features are actually contributing. Now, how to quantify that? So they have developed or they have presented the matrix weight of advice. What is weight of advice? That is defined as the final estimate minus initial estimate by advice minus initial estimate. Now it measures the percentage shift in judgment after advice. So it quantifies how much the participants follow the advice they receive. That means if there is a prediction of if there is a prediction of GDM, because this we are focusing on GDM, so then doctors are giving some advice and patient's lifestyle or medication, those things are changing, and after that again the same patient will report because this is a continuous monitoring system, and then the same model will be used to identify the prediction. And the final estimate and initial estimate. What was the GDN value predicted by the model initially? What was the GDN value predicted by the model? What is the value, the ground truth value, or the value given by the doctor, and what is the predictive values? So just find out a ratio of this to identify the weight of advice and quantify this system. So I just want to show you the way they have shown. So this is the final this feature contribution and example comparison they have shown in that case study. So one is your XAI methods, another is the initial and final advice, that ratio, weight of advice, and this is the situation. You can see the percentage of incorrect and percentage of correct with the p-value 0.429, and this is a much reduced p-value, and you can see the incorrect and correct prediction ratio is also changing. So that's what they have reported in their case study. Now I have some question to the audience that with the discussion of this explainable AI system, those who are working on the research, what all components are actually required for your case? Because I want to make this system more interactive. So first, some questions from the audience side, that which all components you find interesting, because you are listening these lectures for last 2-3 days. Which are components you find interesting? Which are components you identify in these case studies I have mentioned? I have given you 3 case studies. Any question from the audience? Actually, we can identify few more points. What are the areas we can explore using this explainable AI in healthcare? Till now, what I have discussed are the case studies. For the clinical decision making system or CCDS, or for the medical image handling cases or medical data handling cases or feature extractions. But what are the situations where we can focus if we want to explore some new areas or some less explored areas in the deep learning based architecture, what we are using for medical image or medical data processing? I hope all of you are familiar with the deep learning based architectures we are using for different type of applications. I have shown in this table. So, so the portion we are mostly using in case of tabular data, our main point is, our main focus as the developer or as the researcher. I hope it is already discussed that who all are working with the explainable AI or who all are interested with the outcome generated by explainable AI. The people who are working with the medical practitioner, developing the AI-based system which can assist the medical practitioner for taking decision, because there are many situations where the particular expertise is not available. Like we can say there are several histopathological slides which needs special skill and expertise for analysis, which we can develop the AI-based system for analyzing those slides. Similarly, there are in case of biochemistry also, there are several areas, biochemistry, clinical biochemistry. There are several areas where AI-based assistance can help a lot because we don't have that much expertise available in our country. There are experts, but the number is very few, because for developing that skill, they need years to analyze the slides. And that's why these AI-based systems are now coming up. But if you check the literatures, there are several studies done to identify that what type of AI-based systems are in practice for medical practitioners. Till today, it is identified that ML-based systems are already in practice in many cases. As I have shown you the work given mentioned in case 2 and case 3, mostly they have used SHAP. They are working with the tabular data. In some cases, they have used SVM also. So most of the things are ML-based systems. But deep learning-based architectures till now are not that much in practice for real-life scenario. Till now, in research phase, we are using deep learning to analyze the medical data or medical image. Where is the problem? The main problem is when you are predicting, as it is a black box, people are not getting sufficient confidence to use it as a decision-making system. And there comes the requirement that what type of situation you can utilize this explainable AI to justify your design and to justify your outcome. Like when we try to, there are two components in any AI-based system. As a computer science engineer, when you are proposing any new AI-based system or new ANN or CNN models, or you are changing some existing ANN or CNN models, you are claiming it is having higher accuracy, then first you have to justify that what type of what all design you are proposing, whether that is essential for your model or it can be reduced, because always we try to go for a lightweight model to save the cost, reduce the cost, and that is power saving also, that is reducing your complexity of the model also. And if you keep the model simple, definitely performance wise, that is always preferable. So for that, if you want to justify the model, you have to go for ablation study. Remove some of the portions of the model and then check whether your accuracy is getting affected or not. And that is the thing I mentioned in the beginning, that difference between the interpretability and explanation. Interpretable model, if you remove some of the parts, model itself will not work. But if you are going for explainable AI, explainable part is the additional thing. You may do it, may not do it. That is not integral component of the model. Integral component of the model. So explainable part, if you remove also, model will work. And definitely, if I add additional part, it has some cost. So why should we go for, or what type of situation I should go for the explainable? So that is the thing, that when I need not only the accuracy, but to understand that accuracy is achieved based on the features, which are actually the features responsible for that particular prediction or classification. So if I try to understand that part, then I have to go for the explainable part. And you can see here, as I have already mentioned, that feature-based importance, that which all features are important for reaching a particular decision or given a particular classification. This feature importance based explanation or rule based explanation or the prediction, prototype based explanation, these all are basically focusing on the data if available in the tabular form. And this contrafactual based explanation, these are fact finding kind of thing. You are having some decision and then you are cross checking why the decision is achieved. That's the saliency map, the visualization, saliency map visualization for text. This is also used for NLP as well as for medical images and other type of images also. You can identify that which portion of the image is most useful for the particular analysis or particular study. So this type of explanation is very useful, and even in case of time series also, you can go for the different type of AI-based model. And apart from that, these are the approach with respect to the type of data I have. The previous case we have mentioned that what is the type of explanation we can have, the global approach or the local approach. And there can be another thing, that is the design-based approach. You can go to the design-based approach and find out that which design is suitable for your case. Like I have mentioned in one of the slides. Let me switch that one. So this is one situation where you have this is the thing I have mentioned as the saliency map, and you can see the approaches. This is not applied on the medical data, but it's a very interesting observation reported here. Like the original image and the gradient, smart grad, guided backprop, then guided gradcam. Gradcam I have already shown, integrated gradcam and integrated gradients with smooth gradient, and finally gradient with input. So what we are trying to do, if you use the explainable AI part for image and then finally merge it on the input, then only you will be able to identify, because the gradcam will show you which are portions or which are gradient part it is using for performing the prediction or classification. And if you focus on the, if you merge that with the input image, then only you will be able to focus on that which all portions based on the input image the features are used for classification. You can see each of this example. So if we say F is the predictive model and X is the input, then basically we are trying to find out the delta X for each of the cases, because we are trying to compute the gradient. And apart from gradient, another very important thing which is used, tree approach I have already mentioned. Another very important thing which is used is explainability by design. This also can be explored for medical image also, where you identify a neural network to be a set of logical rules or hybrid networks and modify the architecture of a network to make it interpretable. So that can be a self-explainable network. So that's what we are trying to do in case of the global approaches, that we will have parallelly the black box and the white box, and you will perform the aggregate and finally go for the class level, as well as outcome of the white box will give you the explanation part. That's what we are doing in case of this analysis. This is applicable for medical image also. So this is the thing. You can have the concept encoder part. At the same time, you can have the, with similar relevance parameter, you can have the explainable model, and you can calculate the loss here also, and we'll have outcome of the explanation, as well as the final aggregator will give you the class level. Similarly, there are approaches reported long back in 94, then 2018, 2019, where some properties impose some properties that are interpretable neural network should satisfy, like logical consistency, non-contradictory rules, completeness, fidelity of explanation to the model's output, sparsity of high-level concepts, and stability of explanation. So, and then they propose joining two models, one for prediction and other for explanation. So this is true for your classification part also, as well as your explanation prediction part also, where you can join the prediction or classification model with the explanation part and finally come out with the working model. And this is another example, like generating the visual explanation. This was worked out by Hydrins in 2016. And visual explanation, we are familiar with the caption generation for image and caption generation for video. But in this work, he is not going for caption generation only. He has focused on the explanation of the image also. And then this is another interesting example where the particular image, and you can see that which portion of the image is actually contributing to classify this particular part. So that is used, like you can say that this is cardinal because the recurrent explanation generator model, you have LSTM here, and when you are generating, because this is an encoder decoder model, so when you are generating the sentence, each part of this LSTM series, series of connections, it is basically generating one word of your sentence. So which portion is mainly contributing to decide that this is cardinal, that is coming out as the outcome of this explanation. So that was the very interesting study and did by Hendricks in 2016, and similar kind of study can also be done in case of medical images or medical field course, because now there are several situations where open medical image data source available, and you can check and you can start working with the explainable AI, so that you know that you have the ground truth. You know that with the particular data set, if you design a model, if you train the model, you can generate the result. At the same time, you run with any explainable AI algorithm, try to find out that which portion of the input image is actually contributing to the final outcome. And then you will have the idea that how this entire thing is working. So initially, mostly this mainly we are focusing on mostly the post hoc approaches, which are good for existing black box models, which are currently in use, but with some flaws, like provide an explanation, but may not the one used by the model. So that is another challenge, that whether the explanation given by my algorithm, that is the correct explanation which is used by the model. So in many cases, this formal explanation, interpretation and explanation in machine learning, that is basically a rethink machine learning algorithm. Sorry, I at the lens of explainability, that is coming up with the next generation AI tools. 2002, that was a very old paper that time. It was very much celebrated in the science community. Like quantitative biology in 2000 apply somehow. That was the name of the paper, that can biology fix a radio. Similarly, now it is coming up, can statistician provide an explanation? So explanations are currently more interpretations than explanations. And what link with the reasoning, what link with the logics, and what link with the knowledge. So there is a challenge that when you are trying to provide the explanation, there also you have to prove that this explanation are actually, you can quantify that this explanation, comparing two different explanation algorithm, this explanation algorithm is performing much better for this scenario, and it's trying to explain the way the model is working. That is the reason I have shown you the this metric parameter WA, this weight of accuracy or weight of advice in the last case study, where it is they are trying to quantify that how much it is actually working. And making a predictive model explainable, it belongs to more symbolic AI and calls for automated reasoning or knowledge representation, etc. So there are several things, like your contrafactual reasoning. Contrafactual reasoning is not that much used in medical data and image analysis or clinical data analysis till now, but there are scope to use it because there are several situations where the system may not behave as per the expectation. Similarly, the intervention, Bayesian approach, probabilistic programming, knowledge graph, automated reasoning, all are the other parallel ways may be incorporated along with the existing thing. So basically, we all are trying to develop this type of framework, like a framework for learning interpretable network, joint learning of predictor and explainer. This was proposed in 2020 by Parekh et al. So joint learning of F and G, mutual benefits G can even the final predictor. That is the most interesting conclusion. That till now, what all case studies I have mentioned, they are basically using G for explanation. G is not the final predictor. G is used in parallel with F, which is my actual predictor or actual classifier, and G I am using to find out that whether the classifier is using the exact features that should be used or not. But at the same time, there can be some design where you are using the explainer also, which can contribute in your prediction. So predictor F, explainer G, the prediction also you are using. Finally, post hoc or reverse engineering for a predefined network F. That is a framework for learning the interpretability. And I will share this one also. This is a very good set of references given. I have taken many of my sources of slides from these references. So if any of you have any question regarding the topics I discussed, please interact and come up with your comments. Any question from audience? Any of you working with the explainable AI part? Yes, Pallavi, you have any problem with the mic? Can you just share what type of work you are doing with the explainable part? Diabetic retinopathy. Okay. And so basically you are working with the fundus images. So that is also one area, as I have mentioned in the beginning itself, that with the image and the explainable AI, which model you are using? For XAI, which model you are using? Which algorithm? GradCam. GradCam is the very common algorithm you can use. So, anyone else from this group who's working on this domain?
Yes, ma'am. I'm also working on this domain, but it is my initial state. Right
Mhm.
now, just you have given the briefing about Lime and Shapley and PDP and all these. I'm just working on it, and GradCam I'm doing on it. But I'm at the initial phase. I will be
Okay.
probably going with TDSS.
Or medical data or other domain?
Yes, ma'am. Yes, ma'am. I will be preferring the medical data.
So I hope you people are familiar with the utility functions available for this. Okay, any question on the topic we have discussed today? If you have any case studies or you have already.
Ma'am, your presentation was very informative. Kindly share your presentation so
I'll
that
share.
we can just go through once.
Definitely, presentation and the supporting material also, the PDF I have shown at the end. Both I can share. I hope if I share to Professor Bishas, he will circulate down the participants. That will be Professor
Thank you,
Bishas.
ma'am.
Okay, I'll send it to you. Yes, Richa.
Thank you, ma'am, for your support and a
Okay.
very informative lecture.
And some hands-on, those who are interested in this domain, please practice some hands-on and try to find out how it is working. May not be for any specific research problem, but in general, design the model and generate the XAI part and use the functions for XAI to understand. GradCam is one of them, but GradCam is not the only one. So we should explore. Breadcrumbs are easy, but we should explore other techniques also. Okay, then. Thank you. I am closing it here.
Ma'am, please kindly wait. Thank you, ma'am, for such an informative session. I believe I am speaking on the behalf of everyone when I say that this was a really insightful session. As we come to today's end of this enlightening session for today, it is my privilege to extend a heartfelt vote of thanks to you. And it is my pleasure to introduce Professor Shanket Dan, Assistant Professor of the Department of Computer Science and Engineering at JIS College of Engineering. Professor Dan is a remarkable
Yeah.
individual with an
Yes,
exceptional
Igita.
command of
Am I
computer.
audible?
Yes, sir,
Hello.
you're audible.
Okay. Thank you, Ursula Madam, for your wonderful and informative presentation on the fourth day of the session on explainable AI on healthcare. I would like to express my sincere gratitude to each and every participant for making our this program the resounding success. I would like to thanks to our honorable MD Sir, Sardar Tarunjit Singh, and Principal of the JIS, Dr. Partha Sarkar, and also like to thanks Dr. Sitanath Biswas, HOD of the CST, CSC, AIML, and Dr. Vikramjit Sarkar, HOD of the CSE. Dr. Bandyopadhyay described most informative session of on the descriptive what is the application of the expandable AI. thank you, madam, for your good conversation on this meeting. And last of all, to organizing committee, to every organizing committee, I have to describe that your tireless effort and meticulous planning and have created the simplest and productive experience to us. Thank you to all.
Thank you, sir. So I will share my slides. Sitanath sir, I will share my slides. I hope you will be able to share it with the participants. Okay. Thank you then. Explore this region and we will expect more research from you in this domain. Thank you. Thank you. And closing. Thank you.